Hello there, and welcome back. Wherever you are tonight, I'm glad you're here. The world can feel solid and predictable. Floors beneath your feet, air in your lungs, light traveling in straight lines. But beneath that steady surface lies something astonishing. At the smallest scales of existence, reality dissolves into probability, particles blur into waves, and emptiness hums with restless energy. Tonight, we're stepping into that hidden layer together. These are not just facts about quantum physics. They are mind-boggling facts about quantum physics, whispers beyond reality itself. 100 gentle truths about the strange architecture holding everything together. The most relaxing facts about quantum physics to fall asleep to. If you find comfort in these quiet explorations, please consider liking and leaving a comment below. It helps this calm corner of the internet grow, one curious mind at a time. Now, let's move inward, past the surface of things, past what feels solid, down to the smallest layers of existence. Quantum physics is the study of the smallest layers of reality, the scale where atoms and the particles within them quietly govern everything we see. At this level, matter does not behave like solid objects moving predictably through space. Instead, it behaves in ways that feel softer, more fluid, almost dreamlike. The rules that guide planets and falling apples begin to loosen. What replaces them is not chaos, but a subtler framework built from probability and interaction. Quantum physics was born when scientists realized that classical explanations could no longer account for certain tiny behaviors. The very act of looking closer changed what was observed. This science does not replace the world we know, it underlies it. Every chair, every breath, every distant star is shaped by these microscopic rules. Beneath the familiar surface of life, a quieter structure hums steadily, holding reality together. The word quantum comes from the Latin word quantus, meaning how much. It was chosen carefully because at the smallest scales, nature measures things in specific amounts rather than smooth flows. For centuries, energy was assumed to be continuous, like water pouring from a stream. But at the quantum level, energy behaves more like stepping stones than a ramp. It arrives in fixed portions, called quanta, and cannot be divided endlessly. Imagine a staircase where you may stand on one step or another, but never between them. That image captures the heart of quantum theory. This idea did not emerge from philosophy, but from experiments that refused to match classical predictions. The discovery that energy comes in discrete packets reshaped physics completely. It suggested that nature itself has a smallest grain of action, a quiet unit of exchange beneath everything. In the year 1900, German physicist Max Planck faced a stubborn mathematical problem. Experiments showed that heated objects glow in specific ways, yet classical equations predicted impossible results, including infinite energy at short wavelengths. This contradiction became known as the ultraviolet catastrophe. Planck searched for a solution not by overturning physics, but by adjusting a single assumption. He proposed that energy could only be emitted in tiny, fixed amounts rather than continuously. When he inserted this idea into his equations, the predictions suddenly aligned with reality. He did not intend to begin a revolution, he was simply making the mathematics fit observation. Yet, this small shift marked the birth of quantum theory. Planck introduced a constant, now called Planck's constant, that sets the scale for quantum effects. It is extraordinarily small, yet it quietly governs the behavior of light and matter everywhere. Planck's discovery revealed that energy is not infinitely divisible. Instead, it comes in packets so small that we rarely notice them in everyday life. These packets, or quanta, depend on frequency. Higher frequency light carries more energy per packet, while lower frequency light carries less. This explains why ultraviolet light can trigger certain chemical reactions while red light cannot, no matter how bright it becomes. Energy transfer at this scale occurs in whole units. An atom can absorb one quantum or another, but never half of one. This stepping pattern appears again and again throughout quantum phenomena. In daily experience, the packets blend together into smooth motion, just as individual raindrops merge into a steady rainfall. But beneath that smoothness, the stepping remains. Nature, it seems, moves in measured intervals, exchanging energy in careful amounts rather than flowing without boundary. In 1905, Albert Einstein extended Planck's idea in a bold direction. He proposed that light itself behaves not only as a wave but also as discrete particles called photons. This idea emerged from the photoelectric effect, where light striking metal can eject electrons. Classical physics predicted that brighter light should release more energetic electrons. Yet experiments showed that only light above a certain frequency could free them, regardless of brightness. Einstein explained this by suggesting that each photon carries a specific quantum of energy. If the photon's energy is high enough, an electron is released instantly. If not, no amount of intensity helps. This insight revealed that light has a dual character. It can spread like a wave, yet interact like a particle. For this explanation, Einstein received the Nobel Prize, not for relativity, but for showing that light itself comes in packets. In 1913, Niels Bohr applied quantum ideas to the structure of the atom. Classical models suggested electrons orbit the nucleus like planets circling a star. But this created a problem. Orbiting charges should radiate energy and spiral inward. Atoms clearly do not collapse. Bohr proposed that electrons can only occupy specific energy levels. They do not slide gradually between them. Instead, they jump. When an electron moves from a higher level to a lower one, it emits a photon whose energy matches the difference between those levels. This explains why elements emit light at precise colors. Each element has a unique pattern of allowed energy states, creating a spectral fingerprint. The atom, once imagined as a miniature solar system, became something more structured and constrained. Nature allows only certain arrangements, and from those arrangements, chemistry emerges. Soon after light was shown to behave like particles, another insight emerged. In 1924, Louis de Broglie proposed that matter itself possesses wave-like properties. If light can act like particles, perhaps particles can act like waves. Experiments later confirmed this idea. Electrons passing through two narrow slits create interference patterns, just like light waves. Yet when detected individually, each electron lands as a single point. This dual nature is known as wave-particle duality. Quantum objects are not simply one or the other. They exist as probability waves until interaction narrows them into specific outcomes. This is not metaphor, it is measurable. The behavior depends on how the experiment is arranged. When unobserved, particles display wave-like interference. When measured, they behave as localized events. Reality at this scale is shaped by how it is examined. In 1926, Erwin Schrödinger developed an equation that describes how quantum systems evolve over time. The Schrödinger equation does not track solid particles moving along definite paths. Instead, it describes a wave function, a mathematical expression that encodes probabilities. This wave function spreads across space, assigning likelihoods to different outcomes. It evolves smoothly and predictably until an interaction occurs. The equation works with astonishing precision, predicting atomic spectra, chemical bonding, and countless experiments. Yet it does not tell us what the wave function physically is. Is it merely information, or something more tangible? The mathematics remains clear even when interpretation does not. What matters experimentally is that the wave function allows us to calculate probabilities with extraordinary accuracy. At the quantum level, certainty gives way to structured likelihood, guided by elegant equations. Werner Heisenberg showed in 1927 that certain pairs of properties cannot both be known precisely at the same time. Position and momentum form one such pair. The more precisely a particle's position is determined, the less precisely its momentum can be known. This is not a flaw in instruments, it is a fundamental feature of nature. The uncertainty principle arises from the wave-like structure of quantum systems. A tightly localized wave requires a broad range of momenta. This built-in limit means that perfect predictability is impossible at small scales. Even with complete knowledge of the wave function, only probabilities can be given. The future unfolds within constraints, but not with absolute precision. The uncertainty principle reshaped physics, revealing that limits to knowledge are woven into the fabric of reality itself. Superposition is one of the defining features of quantum mechanics. A quantum system can exist in multiple states simultaneously, represented by a combination of possibilities within its wave function. An electron can occupy several energy states at once. A photon can take multiple paths simultaneously. Only when a measurement occurs does one outcome emerge. Before that moment, the system evolves as a blend of alternatives. This is not speculation. It has been demonstrated repeatedly in experiments. Superposition is delicate, easily disrupted by environmental interaction. Yet while it persists, the system behaves as though many futures coexist. In everyday life, decoherence quickly hides these effects. But at microscopic scales, superposition is normal. The world does not commit to a single outcome until interaction forces the choice. Entanglement raised unsettling questions, and in 1964, physicist John Bell found a way to test them. He developed a mathematical inequality that any classical theory with hidden local variables must obey. If particles carried pre-existing instructions determining their behavior independently, their measurement results would follow specific statistical limits. Quantum mechanics predicted stronger correlations. When experiments were finally performed with increasing precision, nature sided with quantum theory. Bell's inequality was violated. This meant that no local hidden variable explanation could account for what entangled particles do. Either influences are not confined by classical locality, or properties are not fully defined before measurement. The universe, at its smallest scales, does not behave like separate pieces interacting only through nearby contact. Instead, something deeper ties outcomes together. This discovery did not just confirm entanglement, it reshaped our understanding of causation. And once locality was questioned, physicists began asking whether classical behavior itself might emerge gradually from something more delicate beneath. If superposition and entanglement are so fundamental, why do we not see them in everyday life? The answer lies in decoherence. When a quantum system interacts with its environment, with air molecules, stray photons, thermal vibrations, information about its state spreads outward. This interaction entangles the system with countless surrounding particles. The delicate interference patterns that define superposition are rapidly destroyed. The system begins to behave classically, not because quantum rules stop applying, but because the quantum coherence becomes scrambled beyond recovery. Decoherence happens astonishingly fast for macroscopic objects. A grain of dust interacting with the environment loses coherent superposition almost instantly. This explains why chairs do not appear in multiple places at once. Yet decoherence does not fully solve the measurement problem. It explains the fading of quantum behavior, not the selection of a single outcome. Still, it bridges microscopic uncertainty and familiar solidity. And once coherence can be preserved deliberately, new possibilities open. By carefully protecting entanglement, physicists discovered they could use it to transfer quantum information from one location to another. Quantum teleportation does not move physical particles through space. Instead, it transfers the state, the full quantum description, of one particle onto another distant particle. The original state is destroyed in the process and recreated elsewhere. This requires entanglement as a resource and classical communication to complete the transfer. Experiments have demonstrated teleportation across laboratory tables, through optical fibers, and even between ground stations and orbiting satellites. What moves is not substance, but information encoded in quantum amplitudes. The identity of a quantum state can leap across space without traveling through it in a conventional way. Teleportation reveals that quantum information behaves differently from classical data. And to understand how information itself is embedded in nature, physicists turned toward a deeper framework: quantum fields. Quantum field theory reframes reality in a profound way. Instead of imagining particles as tiny objects moving through empty space, it describes the universe as composed of fields that exist everywhere. Each type of particle corresponds to a specific field. An electron is not a small bead. It is a localized vibration in the electron field. A photon is a ripple in the electromagnetic field. Even in the absence of particles, these fields persist. They fill all of space continuously. Particles appear when a field vibrates in quantized amounts. This view unifies matter and force under a single language of fields and excitations. It also means that empty space is never truly empty. The fields remain even when quiet. And because fields cannot be perfectly still, subtle fluctuations begin to emerge, leading to one of the strangest consequences of quantum theory, the restless nature of the vacuum itself. In classical thinking, a vacuum is simply nothingness. Remove all particles and space becomes empty and inert. Quantum field theory reveals something different. Even in its lowest energy state, a field cannot have zero energy. Due to the uncertainty principle, there must always be slight fluctuations. These fluctuations give rise to virtual particle pairs that briefly appear and disappear. They cannot be observed directly, but their effects are measurable. For example, they shift atomic energy levels and create subtle forces between objects in vacuum. The Casimir effect, where two metal plates placed close together experience a tiny attractive force, arises from these vacuum fluctuations. Space itself seethes with activity. The void behaves less like a blank canvas and more like a quiet ocean with ripples below the surface. And if space contains energy, then that energy may influence gravity and even the expansion of the universe. According to general relativity, energy affects the curvature of space-time. If the vacuum contains energy, then even empty space can shape cosmic expansion. Observations in 1998 revealed that the universe is not merely expanding, but accelerating. Something is pushing galaxies apart. One candidate explanation is vacuum energy, sometimes associated with dark energy. However, quantum theory predicts an enormous vacuum energy density, vastly larger than what is observed. This mismatch remains one of the greatest unsolved problems in physics. Why does the vacuum contain so little effective energy compared to theoretical expectations? The question sits at the intersection of quantum mechanics and cosmology. It suggests that our understanding of fields and gravity is incomplete. And this tension becomes even more dramatic in extreme environments, such as near black holes. Black holes seem like the ultimate absorbers, allowing nothing to escape. Yet, quantum theory predicts that they emit radiation. Near the event horizon, vacuum fluctuations produce particle pairs. Occasionally, one particle falls into the black hole while the other escapes, appearing as radiation. This process, known as Hawking radiation, causes black holes to lose mass gradually over immense timescales. The radiation is extremely faint for large black holes, but its existence reveals a deep connection between gravity, quantum fields, and thermodynamics. Black holes are not perfectly black. They glow softly against the vacuum. This discovery raises further mysteries about information and entropy. What happens to the information carried by matter that falls into a black hole? The question remains open, and it points toward a deeper ambition in physics, uniting quantum theory and gravity into one coherent framework. Quantum mechanics governs the microscopic world. General relativity governs gravity and cosmic structure, yet the two theories are mathematically incompatible under extreme conditions. At the center of black holes and at the beginning of the universe, both frameworks must apply simultaneously. Quantum gravity aims to reconcile them. Approaches such as string theory, loop quantum gravity, and holographic duality attempt to describe space-time itself in quantum terms. Some theories suggest that space may be composed of discrete units at the Planck scale. Others propose that space-time geometry emerges from patterns of entanglement. Though no final theory has been confirmed, the search continues. The unification of these pillars would reshape our understanding of reality. And hints from cosmology suggest that quantum effects played a crucial role in shaping the earliest moments of existence. In the earliest fractions of a second after the Big Bang, the universe was extraordinarily small and dense. Quantum fluctuations in energy density arose naturally due to uncertainty. During a period called cosmic inflation, space expanded rapidly, stretching these microscopic fluctuations to astronomical scales. Over billions of years, gravity amplified them into galaxies, stars, and clusters. The faint temperature variations seen in the cosmic microwave background radiation are echoes of those original quantum ripples. Every galaxy traces back to quantum noise in the early universe. Structure emerged from uncertainty. The vast cosmic web began as probability fluctuations. This connection between the smallest quantum scales and the largest cosmic structures illustrates how deeply quantum theory permeates reality. And yet, even after a century of discovery, the foundational questions remain. Despite extraordinary predictive success, quantum mechanics still leaves one central puzzle unsolved. Why does a single definite outcome emerge from many possibilities? The equations describe probabilities evolving smoothly. They do not clearly explain the transition to one experienced result. Interpretations vary. The Copenhagen view treats collapse as fundamental. Many worlds proposes branching realities. Collapse models suggest spontaneous reductions. Decoherence explains classical appearance, but not final selection. No experiment has yet resolved which interpretation reflects reality's true structure. The measurement problem is not a minor technical issue, it touches the nature of existence itself. Does reality crystallize only when interaction occurs? Or do all possibilities unfold beyond our perception? The question remains open, quiet, and patient, much like the quantum world itself. If quantum fields give rise to particles, they also predict something unexpected. For every particle, there exists an antiparticle. Antimatter mirrors ordinary matter almost exactly, with identical mass but opposite electric charge and other quantum numbers. When a particle meets its antiparticle, they annihilate, converting their mass into pure energy according to Einstein's equation, E equals mc squared. Antimatter was first predicted mathematically before it was observed, a triumph of theory-guiding experiment. Today, we create antiparticles in accelerators and even use them in medical imaging, such as PET scans. Yet antimatter is rare in the universe. Shortly after the Big Bang, matter and antimatter should have existed in equal amounts. Something subtle tipped the balance, leaving behind the matter that forms stars, planets, and us. Why that imbalance exists remains an open mystery. And to understand the deeper structure of matter itself, we must look even further inward. Protons and neutrons, once thought to be fundamental, are themselves composed of smaller constituents called quarks. Quarks come in different flavors: up, down, charm, strange, top, and bottom, though only the lightest two make up ordinary matter. They are bound together by the strong nuclear force, carried by particles called gluons. Unlike gravity or electromagnetism, the strong force grows stronger as quarks are pulled apart. Attempting to isolate a quark only creates new quark pairs. This phenomenon, known as confinement, ensures quarks are never observed alone. They exist only within composite particles like protons and neutrons. Inside every atom's nucleus, quarks vibrate in a dense, dynamic dance mediated by gluons. This internal structure gives matter its stability. Yet even this is not the end of the story, because mass itself, the property that gives matter weight, arises from something even more subtle. Mass is not an inherent property that particles simply possess. According to the standard model of particle physics, particles acquire mass through interaction with the Higgs field, an invisible field that permeates all of space. As particles move through this field, they experience resistance. That resistance manifests as mass. The Higgs boson, discovered in 2012 at CERN, is a detectable ripple in this field. Its discovery confirmed a decades-old prediction and completed a major piece of the standard model. Without the Higgs field, particles like electrons and quarks would be massless, unable to form stable atoms. The everyday solidity of matter depends on this quiet background field. Yet while the standard model describes known particles and forces with extraordinary accuracy, it does not explain everything. It leaves gravity outside its framework and offers no complete answer to dark matter, reminders that our understanding remains incomplete. When astronomers measure how galaxies rotate, they find something puzzling. The visible matter, stars and gas, does not provide enough gravity to explain their motion. Something unseen exerts additional gravitational pull. This unknown substance is called dark matter. It does not emit or absorb light, and it interacts weakly, if at all, with ordinary matter except through gravity. Experiments on Earth attempt to detect dark matter particles directly, but so far none have been confirmed. Some theories propose entirely new quantum fields to account for it. Others suggest modifications to gravity itself. Whatever its nature, dark matter shapes cosmic structure on the largest scales. Galaxies formed within vast halos of it. This unseen component reminds us that the particles we know may represent only a fraction of what exists. And just as quantum theory reshaped our view of matter once before, it may do so again. At extremely low temperatures, certain materials undergo a transformation. Their electrical resistance drops to zero. This phenomenon is called superconductivity. In this state, electrons pair up into what are known as Cooper pairs. Instead of scattering randomly through a material, these pairs move coherently as a single quantum state. Resistance disappears because the pairs cannot easily be disrupted. Superconductivity allows electrical currents to flow indefinitely without energy loss. It enables MRI machines, particle accelerators, and magnetic levitation trains. At its heart lies quantum mechanics, acting not on a single particle, but on countless particles behaving collectively. The wave functions of electrons overlap and synchronize. This collective behavior shows that quantum effects are not confined to the microscopic world alone. Under the right conditions, they scale upward, and that scalability opens doors to new forms of computation. Classical computers store information as bits, zeros or ones. Quantum computers use quantum bits, or qubits. Unlike classical bits, qubits can exist in superpositions of 0 and 1 simultaneously. This allows them to represent multiple possibilities at once. When several qubits become entangled, their combined state encodes a vast range of possibilities in parallel. Carefully designed quantum algorithms manipulate these probability amplitudes so that incorrect answers interfere destructively while correct ones reinforce. Measurement then reveals the most likely solution. Building stable qubits is extraordinarily challenging. They must be shielded from environmental noise that causes decoherence. Yet even early quantum processors demonstrate capabilities beyond classical simulation in specific tasks. Quantum computing is not about speed in the traditional sense. It is about exploring possibility space differently, and entanglement plays a crucial role in that exploration. Entanglement is not merely a philosophical curiosity, it is a practical resource. In quantum computing, entangled qubits share correlations that cannot be reproduced classically. Operations on one qubit influence its entangled partners, allowing information to be processed in a deeply interconnected way. This interconnectedness enables quantum algorithms to solve certain problems more efficiently than classical ones. Entanglement also underlies quantum cryptography, where secure keys can be distributed with guaranteed detection of eavesdropping. The fragility of entanglement remains a technical hurdle, but researchers continue to improve methods of preserving coherence. As quantum networks expand, entanglement may link distant processors into a global quantum internet. Information itself becomes a physical quantity shaped by quantum laws. And beyond computing and communication, quantum effects may quietly influence living systems as well. Though quantum behavior is most obvious at tiny scales, evidence suggests certain biological systems exploit it. In photosynthesis, energy transfer within plant cells appears to follow quantum coherent pathways, exploring multiple routes to find efficient outcomes. Some migratory birds may use quantum entanglement in specialized proteins to sense Earth's magnetic field. There are even proposals that quantum tunneling plays a role in enzyme activity and possibly in our sense of smell. These ideas are still being tested and refined, yet they suggest that life may have evolved to harness quantum mechanics rather than merely tolerate it. The boundary between physics and biology grows thinner. If quantum principles operate within cells, then the strange rules of probability and coherence are not confined to laboratories. They are woven into living processes, and those same principles reach back to the very origin of cosmic structure. In classical physics, particles must possess enough energy to overcome barriers. Quantum mechanics offers another possibility. Through tunneling, particles have a small probability of passing through barriers they do not have enough energy to climb. This phenomenon allows hydrogen nuclei in the Sun's core to fuse despite their mutual electric repulsion. Without tunneling, fusion would require far higher temperatures. The Sun shines because quantum probability allows unlikely events to occur regularly at enormous scales. Tunneling also enables technologies like scanning tunneling microscopes and certain semiconductor devices. It reminds us that barriers are not absolute at the quantum level. There is always some amplitude beyond the wall. And if particles can tunnel through barriers, then perhaps even space and time themselves may not be continuous in the way we imagine. Some approaches to quantum gravity propose that space is not infinitely divisible. At the Planck scale, around 10 to the power of minus 35 meters, space-time may consist of discrete units. Just as matter is made of atoms, space itself could be composed of fundamental building blocks. In such models, smooth continuity emerges only at larger scales. Detecting this granularity directly remains beyond current technology, yet certain high-energy phenomena might one day reveal subtle signatures. If space is quantized, then geometry itself arises from deeper quantum structures. This idea completes a remarkable arc, from Planck's discovery that energy comes in quanta to the possibility that space-time itself does as well. The smallest units of nature may define not only matter and light, but the very stage on which they appear. And with that realization, the quantum story grows quieter, yet deeper. As quantum mechanics matured, physicists sought to understand what its mathematics truly meant. The Copenhagen interpretation, developed in the 1920s by Niels Bohr and Werner Heisenberg, became the most widely taught explanation. It proposes that a quantum system does not possess definite properties until it is measured. Before measurement, it exists in a superposition described by a wave function. When observed, the wave function collapses into a single outcome. This interpretation does not attempt to describe what really happens between measurements. Instead, it focuses on predicting experimental results. It treats collapse as a fundamental feature of nature. Many physicists adopted this pragmatic stance because it works, yet it leaves a lingering unease. What does it mean for reality to lack definite properties until interaction occurs? This discomfort inspired alternative interpretations, each attempting to smooth the strangeness in its own way. In 1957, Hugh Everett proposed a radical alternative. Rather than assuming the wave function collapses, the many worlds interpretation suggests that it never does. Every possible outcome encoded in the wave function occurs, but in separate, branching realities. When a quantum event with multiple possibilities unfolds, the universe splits into parallel branches, each containing a different result. In one branch, a particle spins up. In another, it spins down. Observers also branch, experiencing only one outcome in their respective reality. This interpretation preserves the smooth mathematical evolution of the wave function, avoiding mysterious collapse. However, it raises staggering philosophical questions. If all outcomes occur, what does probability mean? Are there countless versions of ourselves diverging at every quantum event? Many worlds offers elegance in mathematics, but at the cost of multiplying realities. And for those uneasy with branching universes, other interpretations provide different comforts. Pilot wave theory, also called Bohmian mechanics, offers a more deterministic picture. In this interpretation, particles always possess definite positions and trajectories. A guiding wave, the pilot wave, evolves according to Schrödinger's equation and directs particle motion. The wave spreads through space, influencing where particles move, even across distances. Unlike Copenhagen, there is no collapse. Unlike many worlds, there is no branching universe. Instead, hidden variables determine outcomes precisely. However, pilot wave theory requires accepting non-locality. The guiding wave can instantaneously influence distant particles. Though mathematically equivalent to standard quantum mechanics in predictions, it shifts the philosophical burden. It replaces randomness with hidden structure. For some, this restores comfort. For others, it complicates simplicity. And still, alternative proposals suggest that collapse might occur physically, without observers or branching universes. Collapse theories propose that superpositions do not persist indefinitely. Instead, they spontaneously reduce into definite states after a certain time or at certain scales. In these models, collapse is a real physical process built into nature. For microscopic particles, collapse events are rare, allowing superposition to dominate. For macroscopic objects, collapse happens rapidly, explaining why we do not observe large-scale superpositions. These theories aim to bridge quantum and classical worlds without invoking observers or parallel universes. Experiments are ongoing to test whether spontaneous collapse produces tiny detectable energy signatures. So far, results remain inconclusive. Collapse models remind us that interpretation is not merely philosophy, it guides experimental design. And beyond interpretation lies another shift, not about collapse, but about logic itself. Classical logic operates on clear binaries. A statement is true or false. An object is here or there. Quantum logic is more subtle. The order in which properties are measured can affect outcomes. Certain propositions cannot be assigned definite truth values simultaneously. The mathematical structure underlying quantum mechanics, Hilbert space, allows for probabilities that interfere constructively and destructively. This means that outcomes are not simply weighted alternatives. They can combine in ways that alter likelihood. In quantum logic, the structure of reasoning itself changes. Events cannot always be described independently of measurement context. This departure from classical intuition is one reason quantum mechanics feels alien. It challenges not just physical expectation but logical expectation, and when logic softens, certainty softens with it. In classical physics, randomness signals incomplete knowledge. If we knew every detail, we could predict everything precisely. Quantum mechanics challenges this view. Even with complete knowledge of the wave function, only probabilities can be predicted. The decay of a radioactive atom, the spin of a measured electron, these events occur without deeper deterministic cause, at least within current theory. Some interpretations preserve hidden determinism. Others accept randomness as fundamental. Experiments testing Bell's inequalities support the absence of local hidden variables. This suggests that unpredictability is not merely ignorance, it is woven into reality's fabric. For some, this is unsettling. For others, it allows novelty within physical law. And this interplay between order and unpredictability extends beyond particles into thermodynamics. Thermodynamics describes heat, energy flow, and entropy at large scales. Quantum thermodynamics studies how these concepts arise from microscopic quantum rules. At small scales, fluctuations become significant. Energy exchange can occur in discrete jumps. Even temperature becomes a statistical property emerging from quantum probabilities. Researchers investigate how entropy behaves in entangled systems and how quantum coherence influences energy efficiency. Some quantum engines have been built in laboratories, exploring whether quantum effects can surpass classical efficiency limits. The relationship between information and entropy grows especially intriguing. In quantum systems, information itself carries thermodynamic consequences, and nowhere is the connection between entropy, information, and gravity more dramatic than in black holes. Black holes possess entropy proportional to the area of their event horizon. This insight, developed by Jacob Bekenstein and Stephen Hawking, suggests that information about everything that falls into a black hole may be encoded on its surface. This idea inspired the holographic principle, the proposal that the information describing a volume of space can be represented on its boundary. In certain theoretical frameworks, the geometry of space-time itself may emerge from quantum entanglement patterns. If true, space is not fundamental. It arises from information relationships. Entanglement could be the scaffolding of geometry. This remarkable possibility blurs distinctions between physics and information theory, and it suggests that at the deepest level the universe may be structured less like a collection of objects and more like a network of correlations. In certain materials, quantum states depend not on local properties but on global topological features. These topological states are remarkably robust. They resist disturbance from impurities or minor defects. The quantum Hall effect revealed such quantized behavior, where electrical resistance appears in precise integer or fractional steps. These effects arise from collective quantum organization of electrons under strong magnetic fields. Because topological states are protected by mathematical structure, they are promising for building stable qubits resistant to decoherence. Topology introduces geometry into quantum behavior. It shows that abstract mathematical ideas can shape tangible material properties, and that resilience offers hope for building more reliable quantum technologies. When certain atoms are cooled to temperatures just above absolute zero, they can enter a phase known as a Bose-Einstein condensate. In this state, individual atoms lose their separate identities. Their wave functions overlap and merge into a single coherent quantum state. The entire collection behaves as one unified entity. This allows scientists to observe quantum effects on a macroscopic scale, interference patterns visible to the eye, superfluid flow without viscosity. Bose-Einstein condensates demonstrate that quantum mechanics is not confined to the tiny. Under carefully controlled conditions, coherence scales upward. The boundary between microscopic and macroscopic softens. And as quantum coherence expands, so does our sense of what reality permits. Under extremely low temperatures, certain liquids enter a phase called a superfluid. Liquid helium is the most famous example. When cooled below about 2 degrees above absolute zero, helium loses all internal friction. It can flow endlessly through tiny channels without slowing. It can creep up the walls of a container against gravity, forming a thin film that escapes over the edge. This behavior arises because the helium atoms occupy the same quantum state, moving together as a single coherent wave. The liquid no longer behaves as separate particles colliding randomly. Instead, it behaves as a unified quantum entity. Superfluidity demonstrates how quantum mechanics can dominate at macroscopic scales when thermal disturbances are minimized. And from superfluidity, another astonishing phenomenon naturally follows: the ability to suspend objects without contact. When superconductors are cooled below their critical temperature and placed above magnets, they can levitate in stable positions. This effect combines superconductivity with magnetic field pinning. A superconductor expels magnetic fields from its interior, the Meissner effect, but it can also trap magnetic field lines in fixed configurations. The result is not simple floating, but locked suspension. The object resists motion even when tilted or inverted. It appears almost glued in mid-air. This dramatic demonstration arises from quantum coherence acting collectively across many electrons. Though it feels like magic, it is precise physics at work. Quantum levitation hints at future frictionless transport and energy-efficient systems. And just as superconductors rely on delicate quantum effects, so too do devices that allow us to measure nature with extraordinary precision. The most accurate clocks ever built rely on quantum transitions within atoms. When atoms such as cesium or ytterbium change energy levels, they emit or absorb radiation at extremely precise frequencies. Atomic clocks count these oscillations. Because quantum transitions are identical everywhere in the universe, they provide a stable reference. The best atomic clocks would lose less than a second over billions of years. This precision is not merely academic. GPS navigation depends on atomic clocks aboard satellites. Telecommunications and scientific experiments rely on their accuracy. As technology improves, new optical lattice clocks measure time so precisely they can detect minute changes in gravitational potential. Time itself becomes a measurable quantum vibration, and such precision extends beyond clocks into sensing the faintest whispers of physical change. Quantum sensors exploit superposition and entanglement to measure quantities with extraordinary sensitivity. They can detect minute magnetic fields, tiny accelerations, and slight variations in gravity. Some use clouds of ultra-cold atoms suspended by lasers. Others rely on defects in diamonds known as nitrogen vacancy centers. These devices can measure changes far too small for classical instruments. Quantum sensing may improve navigation without GPS, map underground structures, and detect subtle brain activity. In each case, delicate quantum coherence enhances sensitivity. This precision reveals that quantum effects are not confined to exotic laboratories. They quietly enhance practical tools. And as sensing sharpens, our picture of the cosmos becomes clearer, including glimpses of the universe's earliest light. About 380,000 years after the Big Bang, the universe cooled enough for light to travel freely. That ancient light still fills space as the cosmic microwave background. Tiny temperature variations within it reflect density fluctuations from the early universe. Those fluctuations originated as quantum variations in the inflationary field, stretched to cosmic scales during rapid expansion. The faint mottled pattern seen in microwave maps is a magnified imprint of quantum uncertainty from the universe's infancy. Galaxies later formed in regions where those fluctuations were slightly denser. The largest cosmic structures trace back to microscopic quantum events. The link between the smallest scales and the vastest structures becomes visible in the sky, and inflation itself arises from an extraordinary burst of early cosmic growth. Inflation theory proposes that the universe underwent exponential expansion in a fraction of a second after the Big Bang. During this expansion, quantum fluctuations in energy density were stretched enormously. What began as subatomic variations became the seeds of cosmic structure. Inflation explains why the universe appears remarkably uniform on large scales while still containing subtle variations. The rapid expansion smoothed space while preserving tiny irregularities. These irregularities later grew under gravity into stars and galaxies. Without inflation, the cosmos might look very different. The interplay between quantum uncertainty and cosmic expansion shaped everything visible today. And yet, even as the universe grew vast, mysterious forces continued to influence its expansion. In 1998, astronomers discovered that the universe's expansion is accelerating. Instead of slowing under gravity, galaxies drift apart faster over time. This acceleration is attributed to dark energy, a pervasive influence that exerts repulsive gravitational effects. One possibility is that dark energy corresponds to vacuum energy from quantum fields. If empty space contains energy, it can drive expansion. However, theoretical calculations of vacuum energy predict far more than observed. The discrepancy remains unresolved. Dark energy constitutes most of the universe's energy budget, yet its nature remains unknown. It reminds us that quantum theory, cosmology, and gravity remain incomplete, and this tension motivates the search for quantum gravity. One approach to quantum gravity, called loop quantum gravity, proposes that space-time itself is quantized. Instead of being continuous, space consists of tiny discrete loops woven into a network. These loops define minimum units of area and volume. At scales near the Planck length, geometry may resemble a granular fabric. Smooth space-time emerges only at larger scales. In this view, gravity arises from the geometry of these loops rather than from a force carried by particles. While still theoretical, loop quantum gravity provides a mathematical framework attempting to merge quantum principles with Einstein's relativity. If space is discrete, then continuity is an approximation. And alongside this idea, another framework offers a very different perspective. String theory suggests that fundamental particles are not point-like objects, but tiny vibrating strings. Different vibrational modes correspond to different particles. An electron is one pattern of vibration, a photon is another. String theory requires additional spatial dimensions beyond the familiar three. These extra dimensions may be compactified at scales too small to detect directly. The theory elegantly incorporates gravity by including a vibrational mode corresponding to the graviton. Though experimentally unconfirmed, string theory provides a consistent mathematical framework unifying forces and particles. It replaces particles with harmonics of a deeper structure. And whether through strings, loops, or some future insight, the quest for unification continues. Quantum mechanics and general relativity both describe nature with extraordinary success, yet they remain mathematically incompatible in extreme regimes. Black hole singularities and the earliest moments of the universe demand a theory that merges them. Whether the answer lies in strings, loops, holography, or an entirely new idea, the search reflects humanity's desire for coherence. Quantum physics has revealed that certainty softens at small scales. Gravity has shown that space-time bends. Somewhere beneath both may lie a deeper simplicity. The unification of forces would not eliminate mystery, it would deepen it. And as we rest within these layered ideas, the quantum world continues quietly, subtle, probabilistic, and endlessly unfolding. In classical life, watching something does not stop it from evolving. In quantum mechanics, frequent observation can slow or even halt change. This phenomenon is called the quantum Zeno effect. When a quantum system is measured repeatedly in rapid succession, its wave function continually collapses back to its initial state. Each measurement interrupts its natural evolution. In experiments with atoms and photons, scientists have demonstrated that constant observation can suppress transitions that would otherwise occur. It is as though the system is reset before it can fully change. The name comes from Zeno's paradoxes, where motion seems impossible when divided into infinite steps. Here, repeated measurement divides time into fragments so small that transformation is inhibited. This effect reveals again that measurement is not passive, it shapes behavior. And once scientists learned to manipulate quantum states so precisely, new tools emerged for building circuits based entirely on quantum principles. A Josephson junction consists of two superconductors separated by a thin insulating barrier. In classical physics, electrons should not cross this barrier without applied energy, but quantum tunneling allows paired electrons, called Cooper pairs, to pass through effortlessly. This tunneling produces a supercurrent that can oscillate with extraordinary precision when voltage is applied. Josephson junctions form the backbone of many superconducting qubits used in quantum computers. They also power ultra-sensitive magnetic detectors known as squids, capable of measuring minute magnetic fields, even those produced by the human brain. What once seemed a strange theoretical possibility, tunneling through barriers, now forms the basis of practical devices. And these devices connect not just components, but potentially entire networks. Just as classical computers are connected by the internet, quantum processors may one day be linked by quantum networks. These networks would distribute entanglement across distances, enabling quantum teleportation of states and secure communication. Unlike classical data, quantum information cannot be copied without disturbance. This property ensures security in quantum key distribution systems. Researchers have already transmitted entangled photons between ground stations and orbiting satellites, demonstrating the feasibility of long-distance quantum links. Quantum repeaters are being developed to preserve entanglement across extended distances. A future quantum internet would not merely transmit information, it would distribute quantum states themselves. And as networks grow, the connection between entanglement and geometry begins to appear more profound. A bold conjecture proposed by physicists Leonard Susskind and Juan Maldacena suggests that entangled particles may be connected by tiny, non-traversable wormholes. The idea is summarized as ER equals EPR, linking Einstein-Rosen bridges, wormholes, with Einstein-Podolsky-Rosen entanglement. In this view, space-time geometry and quantum entanglement are two expressions of the same underlying structure. While these wormholes would not allow travel or communication, they represent a geometric interpretation of entanglement. This proposal bridges general relativity and quantum mechanics in a surprising way. It hints that space-time itself may emerge from patterns of entanglement. If so, geometry is not fundamental. It arises from deeper informational relationships. And this idea reshapes how we think about distance. Some theoretical frameworks suggest that space-time is not a basic ingredient of reality. Instead, it emerges from entanglement networks. Studies in holographic duality and tensor networks show that geometric relationships can arise from patterns of quantum correlations. In certain models, reducing entanglement causes space-time geometry to weaken or fragment. Distance itself may reflect the degree of entanglement between regions. In this picture, the universe is less like a container holding objects and more like a web woven from information. If entanglement defines connectivity, then separation is secondary. Geometry becomes a macroscopic manifestation of microscopic relationships. And this perspective reframes one of the most persistent puzzles in physics, the black hole information paradox. Black holes appear to erase information when matter falls into them. Yet quantum mechanics insists that information cannot be destroyed. Hawking radiation suggests that black holes evaporate over time, leaving behind radiation that seems random. If information truly disappears, quantum theory would be violated. This contradiction is known as the black hole information paradox. Many proposals attempt to resolve it. Some suggest information escapes subtly in Hawking radiation. Others invoke holographic principles or quantum corrections at the event horizon. The paradox has driven decades of theoretical research. It sits at the crossroads of gravity, thermodynamics, and quantum mechanics. Solving it may reveal how space-time and information are intertwined, and that connection leads naturally to a broader insight about entropy and knowledge. Entropy measures disorder in thermodynamics, but it also measures missing information. In quantum systems, entropy reflects uncertainty about a system's state. Entangled systems can exhibit entanglement entropy, where parts of a system carry information about one another. This concept links quantum theory with information theory. The famous equation describing black hole entropy shows that surface area encodes informational content. This connection suggests that physics at its core may be about information, how it is stored, transformed, and conserved. The laws governing matter and energy may simultaneously govern bits of knowledge. As information flows through the universe, it shapes structure and behavior. And in this light, quantum mechanics becomes not just a theory of particles, but a theory of information itself. To protect fragile quantum states in computers, scientists use quantum error correction. These protocols distribute information across entangled qubits so that damage to one part does not destroy the whole. Interestingly, similar mathematical structures appear in certain models of space-time geometry. Some researchers suggest that space-time stability may resemble quantum error correction codes. Just as encoded information survives local disturbances, geometric structure may persist despite fluctuations. This parallel strengthens the idea that space-time could emerge from informational principles. The mathematics linking error correction and holography hints that the universe preserves structure through redundancy and entanglement. And as coherence protects fragile quantum systems, certain materials display remarkable resistance to disruption. One of the greatest challenges in quantum computing is protecting qubits from decoherence. Topological qubits offer a potential solution. In certain exotic materials, quasi-particles known as anyons exhibit topological properties. Their quantum states depend on braiding patterns rather than local details. Because topology is global, minor disturbances do not easily alter the encoded information. This makes topological qubits inherently robust against noise. Though still under development, this approach could dramatically improve quantum stability. Topology once again reveals how abstract mathematics shapes physical behavior. It suggests that resilience can arise from structure rather than force, and resilience leads us back to fundamental matter, the strange, indivisible building blocks beneath it all. The Standard Model describes quarks, leptons, and force carriers with extraordinary precision. Yet it does not explain why these particles exist in their specific families or why their masses take the values they do. Some theories suggest they may be excitations of deeper underlying structures, perhaps strings, loops, or other entities yet undiscovered. The search continues for particles beyond the Standard Model, including candidates for dark matter. Each new experiment at high-energy accelerators probes deeper layers of reality. The journey that began with Planck's energy quanta continues toward deeper foundations, and even as experiments refine knowledge, the philosophical questions remain quiet companions. In classical thinking, probability measures ignorance. If we flip a coin, it lands heads or tails because of forces we could, in principle, calculate. Quantum probability is different. Even with complete knowledge of a system's wave function, we can predict only the likelihood of outcomes. The probabilities are not placeholders for missing detail. They are built into the structure of reality itself. The wave function evolves deterministically, but measurement yields a specific result chosen according to probability amplitudes. This subtle balance, deterministic evolution followed by probabilistic outcome, gives quantum mechanics its distinctive character. It suggests that certainty exists only at the level of equations, not events. And this invites a deeper question. If probability is fundamental, what does that mean for causation itself? In everyday life, causes precede effects in clear linear chains. Push a glass and it falls. Heat water and it boils. In the quantum realm, causation becomes less rigid. Certain experiments suggest that the order of events can become ambiguous under specific conditions. In quantum delayed choice experiments, decisions made after a particle passes through an apparatus appear to influence how its earlier behavior is described. This does not allow backward communication in time, but it does blur the neat classical picture of cause and effect. The quantum formalism allows for correlations that defy simple sequencing. Reality at small scales is less like a line of dominoes and more like an interconnected web. And when webs replace chains, our understanding of knowledge itself must adapt. Quantum theory forces us to reconsider the relationship between what is known and what is. The wave function encodes probabilities of outcomes. But does it represent physical reality or only information about possible measurements? Some physicists argue that the wave function is epistemic, about knowledge. Others argue it is ontic, about reality itself. Experiments testing quantum state realism suggest that the wave function cannot be purely informational. Yet debate continues. The boundary between description and existence softens. In classical physics, measurement reveals pre-existing properties. In quantum mechanics, measurement participates in defining them. This participation does not mean human consciousness shapes the universe in a mystical sense. It means interaction defines outcome, and interaction leads us toward the quiet question of awareness. Popular discussions sometimes suggest that consciousness collapses the wave function. While early thinkers speculated along these lines, most physicists today favor explanations rooted in physical interaction and decoherence. There is no experimental evidence that human awareness is required for quantum collapse. Detectors, not minds, trigger measurable outcomes. Still, the philosophical tension lingers. Quantum mechanics leaves open profound questions about observation, information, and existence. Consciousness remains one of the great unsolved puzzles of science, but it lies beyond current quantum theory. Physics does not yet explain subjective experience. It describes correlations, probabilities, and fields. And this distinction between describing behavior and explaining experience reminds us of the limits of any scientific framework. The uncertainty principle sets quantitative limits on simultaneous knowledge of certain properties. But beyond that, quantum theory suggests deeper epistemic boundaries. No measurement can reveal all aspects of a system at once. Complementarity, a concept introduced by Niels Bohr, holds that some properties can only be understood through mutually exclusive experimental setups. Light behaves as a wave in one context and as a particle in another. Both descriptions are necessary, yet cannot be observed simultaneously. Reality allows multiple complementary views. This principle invites intellectual humility. Our descriptions are contextual, shaped by how we ask questions. The world does not yield all its features in a single frame, and this humility opens space for wonder rather than frustration. It may be tempting to equate quantum uncertainty with disorder, but uncertainty does not mean absence of structure. The Schrödinger equation evolves with strict mathematical order. Probabilities interfere according to precise rules. Quantum systems obey symmetries and conservation laws. Uncertainty defines limits, not anarchy. Beneath unpredictability lies deep regularity. The patterns of atomic spectra, the stability of matter, the behavior of semiconductors all depend on quantum consistency. The unpredictability of individual events coexists with the reliability of statistical outcomes. In large numbers, quantum randomness produces stable averages. From probabilistic foundations arises dependable structure. And that coexistence of unpredictability and stability reflects something profound about nature. The solid world we experience, chairs, oceans, mountains, emerges from quantum interactions among countless particles. Decoherence suppresses interference at macroscopic scales. Statistical averaging smooths randomness into predictability. The classical world is not separate from the quantum one, it is its large-scale expression. The sharpness of everyday objects is a consequence of overwhelming environmental interaction. The fuzziness at small scales becomes negligible when multiplied by astronomical numbers of particles. Quantum theory does not undermine reality, it underlies it. The stability of chemistry, biology, and engineering arises from quantum rules, and understanding this continuity softens the perceived divide between the strange and the familiar. Every atom in your body follows quantum laws. The electrons that hold molecules together obey the Schrödinger equation. The photons that strike your eyes travel as quantized packets. The neurons that transmit signals rely on quantum chemistry. Though decoherence prevents you from experiencing superpositions directly, the foundation of your biological processes rests on quantum mechanics. You are not outside the quantum world observing it. You are an emergent expression of it. The same probabilistic laws governing stars and atoms shape your cells and thoughts, and this continuity offers a gentle perspective. The quantum realm is not alien, it is intimate. Despite a century of success, quantum mechanics leaves unanswered questions. Why these constants? Why these particle families? Why does measurement produce definite outcomes? Why is vacuum energy so small? Each solved puzzle reveals deeper ones. The history of physics shows that mystery is not a flaw but a frontier. The absence of final answers does not weaken science, it strengthens it. The quantum world remains mathematically precise yet conceptually open. Its equations guide technology and predict experiments flawlessly. Yet interpretation invites ongoing exploration. This balance between clarity and uncertainty creates a quiet intellectual humility. Quantum mechanics is not finished. New experiments probe ever smaller scales and ever higher energies. Quantum computing advances steadily. Cosmological measurements refine our picture of the early universe. Theoretical frameworks evolve. The search for quantum gravity continues. Each generation inherits questions and adds insights. The story that began with Planck's quanta in 1900 continues into the present moment. It is a living theory, refined and tested daily. And as it unfolds, it reshapes not only physics, but philosophy, technology, and our sense of place in the cosmos. It may seem astonishing that rules governing subatomic particles could determine the shape of galaxies. Yet, quantum fluctuations in the early universe seeded the cosmic web. The atoms in your body formed from nuclear reactions enabled by quantum tunneling. The stability of stars, the chemistry of life, and the structure of matter all trace back to probability amplitudes and wave functions. What feels microscopic and abstract quietly shapes the grandest scales imaginable. The smallest vibrations ripple outward into cosmic architecture. There is no true separation between micro and macro, only scale. And once that continuity is seen, the universe feels less like layered compartments and more like one coherent unfolding. That coherence invites a deeper reflection on unity itself. Entanglement suggests that particles once interacting remain described by a shared state, even when separated by great distances. Some theoretical frameworks extend this idea further, proposing that space-time geometry itself emerges from entanglement networks. If so, separateness is not fundamental, it arises from perspective and scale. At deeper layers, the universe may be a continuous informational structure rather than a collection of isolated objects. This does not erase individuality, but it reframes it. Local experiences arise from global structure. Just as waves on an ocean appear distinct yet belong to the same water, physical objects may be localized expressions of deeper unity. And within that unity, uncertainty plays a graceful role. If the universe were perfectly deterministic, novelty would be illusion. Quantum uncertainty allows possibility space to remain open. Each measurement selects an outcome from many. Though probabilities constrain results, they do not dictate a single path in advance. This openness is not chaos, it is structured flexibility. Without quantum indeterminacy, stars might not ignite at the right rates, chemical bonds might not behave as they do, and biological complexity might not emerge. Probability is not weakness, it is creative potential embedded in law. And this interplay between structure and openness mirrors something familiar in experience itself, the balance between predictability and surprise. Though individual quantum events are unpredictable, large numbers create reliable patterns. Radioactive decay rates follow precise exponential curves. Thermal behavior stabilizes into statistical averages. Chemistry becomes dependable. The classical world emerges not by eliminating uncertainty, but by averaging it. Billions upon billions of probabilistic interactions produce stable regularities. From randomness arises reliability. This paradox, unpredictability yielding order, defines the bridge between quantum mechanics and daily life, and it reminds us that certainty at one scale may rest upon uncertainty at another. For all its conceptual strangeness, quantum mechanics rests on compact mathematics. The Schrödinger equation fits on a single line. The commutation relations are elegantly concise. The symmetry principles underlying particle physics are expressed in precise group structures. Beneath interpretive debates lies mathematical clarity. The equations describe phenomena with astonishing accuracy. Beauty in physics often signals truth, not aesthetic beauty alone, but structural economy. The laws governing electrons in atoms also govern semiconductors and stars. Simplicity scales upward, and in that elegance there is quiet reassurance. Quantum mechanics leaves foundational questions unresolved, yet unresolved does not mean broken, it means incomplete. Every scientific theory refines rather than concludes. The fact that the measurement problem persists does not undermine the theory's predictive power. Instead, it highlights the difference between calculation and interpretation. Science often advances by holding paradox patiently. The discomfort of not knowing can coexist with the reliability of what is known. This tension is not weakness, it is movement, and movement, even when subtle, is part of growth. Quantum mechanics reveals deep structure beneath appearances. It shows that matter has layers, that light has dual identity, that space may emerge from information. Yet each answer opens further questions. The universe proves knowable in part, yet inexhaustible in total. Complete closure remains beyond reach. This is not a flaw of intellect, but a feature of reality's depth. There will always be further layers to explore, and that endless horizon gives science its quiet continuity. In quantum physics, to observe is to interact. There is no detached vantage point outside reality. Measuring devices are physical systems obeying the same laws as the particles they detect. This dissolves the illusion of separation between observer and observed. The universe studies itself through interaction. Outcomes arise not from isolated objects, but from relationships. This relational perspective shifts emphasis from things to processes. And in processes, continuity matters more than boundaries. Empty space, once imagined as void, contains fluctuating fields and latent energy. Virtual particles flicker briefly into existence. Vacuum energy influences cosmic expansion. Black holes radiate through quantum effects. Even nothing carries structure. The background of existence is not blank, it is dynamic and layered. This realization reframes emptiness as potential rather than absence. Silence contains vibration, stillness contains movement, and that subtle liveliness continues whether observed or not. Nothing in quantum mechanics requires spectacle, no flashing lights or dramatic events. The quantum world unfolds constantly and calmly beneath perception. Electrons orbit, photons travel, fields fluctuate. The mathematics hums quietly in atoms and stars. Most of these processes remain unnoticed, yet they sustain everything. The extraordinary is continuous and ordinary at once, and this constancy provides a gentle comfort. Reality does not need to announce its depth to possess it. When we speak of atoms and galaxies, it can feel as though we are describing two different worlds. One is unimaginably small, the other impossibly vast. Yet, quantum mechanics teaches us that the laws governing both are not separate. What changes is not the rule, but the scale at which the rule becomes visible. At microscopic levels, uncertainty and superposition can be measured directly. At macroscopic levels, those same effects are averaged out through interaction with the environment. The apparent solidity of a mountain or the predictable motion of a planet does not contradict quantum mechanics. It reflects the statistical blending of countless quantum events. Decoherence smooths probability into stability. The classical world emerges as a large-scale approximation of quantum behavior. Nothing fundamentally new is added. Instead, complexity amplifies and refines what was already there. The smallest equations quietly scale upward, shaping everything from dust grains to spiral galaxies. Classical physics feels solid and dependable because it describes the collective behavior of enormous numbers of particles. When trillions upon trillions of quantum events occur together, their uncertainties cancel into averages. A single molecule moves unpredictably, but a cloud of gas obeys clear thermodynamic laws. A single radioactive atom decays randomly, yet a large sample follows an exact half-life curve. This transformation from randomness to reliability is not accidental. It is statistical law. Quantum mechanics does not undermine classical predictability. It explains its origin. The equations governing probability amplitudes scale into stable macroscopic behavior when systems grow large. The world of falling apples and orbiting moons is not separate from quantum theory. It is what quantum theory looks like when numbers become immense. The strange becomes smooth, the uncertain becomes dependable, and the deeper structure remains present, even when hidden beneath overwhelming averages. The stability of matter depends not on rigid determinism, but on quantum constraints operating across vast assemblies of particles. Electrons occupy quantized energy levels because of wave behavior. The Pauli exclusion principle prevents identical fermions from collapsing into identical states. These restrictions shape atomic structure, chemistry, and material strength. One electron's behavior may be probabilistic, but billions interacting within an atom produce consistent bonds. Those bonds scale into molecules, cells, and solid materials. The solidity you feel when you press your hand against a surface arises from quantum exclusion and electromagnetic repulsion at microscopic levels. Stability is not the absence of motion, it is motion balanced precisely. At every moment, electrons shift, vibrate, and exchange photons, yet the overall structure persists. That persistence is a triumph of quantum organization. And it reveals that what feels firm and continuous is sustained by ceaseless microscopic activity. Every photon that reaches your eyes is a quantum event completing a journey. Some photons have traveled only a few meters from a lamp. Others have crossed billions of light years from distant galaxies. Each one carries information encoded in frequency, polarization, and phase. Quantum mechanics governs how photons are emitted from atoms, how they propagate through space, and how they are absorbed by detectors. The cosmic microwave background, the afterglow of the early universe, consists of photons that have traveled for nearly 14 billion years. Their subtle temperature variations reflect quantum fluctuations from the first moments after the Big Bang. Light is not merely illumination, it is a messenger shaped by quantum law. Across unimaginable distances, discrete quanta bridge separation. The universe communicates with itself through packets of energy, each obeying the same principles discovered in laboratory experiments more than a century ago. Among the most consequential quantum rules is the Pauli exclusion principle. It states that no two identical fermions can occupy the same quantum state simultaneously. This single restriction shapes the periodic table and determines the structure of atoms. Because electrons cannot collapse into identical states, they fill distinct energy levels around nuclei. This arrangement produces chemical diversity, allowing atoms to bond in complex ways. Without the exclusion principle, electrons would crowd into the lowest possible energy state. Matter would compress dramatically. Atoms would shrink. Chemistry would collapse into simplicity. Instead, constraint produces richness. The solidity of matter, the architecture of molecules, and even the structure of white dwarf stars depend on exclusion. It is a limit that creates possibility. Through restriction, the universe generates complexity. Through constraint, it sustains form. Earlier, we spoke about particles as ripples. To go deeper, we must shift perspective entirely. According to quantum field theory, the universe is not made of particles floating in empty space. It is made of fields that exist everywhere. Even in what we call vacuum, these fields remain present. An electron is not a tiny marble traveling through nothingness. It is a localized excitation in the electron field. A photon is a vibration in the electromagnetic field. Every point in space contains these fields, quietly humming whether or not a particle is currently visible. What we perceive as matter is simply where the vibration rises high enough to be detected. The distinction between something and nothing becomes softer here. The fields are constant. Particles are temporary events within them. Reality, at its foundation, is continuous and dynamic. Space is not empty. It is structured by invisible layers of possibility waiting to ripple. Once we understand fields, forces become less mysterious. In classical physics, forces appear as pushes and pulls acting across distance. In quantum theory, forces arise from particle exchanges between fields. When two charged particles repel, they are exchanging virtual photons, brief excitations of the electromagnetic field. When quarks bind inside protons, gluons, excitations of the strong field, mediate that bond. These exchanges do not resemble classical objects flying back and forth in a simple sense. They are fluctuations encoded in mathematical symmetries, yet their effects are measurable. Every attraction, every repulsion, every structural bond in matter emerges from these quantum interactions. Even gravity, though not yet fully described in quantum terms, is suspected to operate through similar principles at deep scales. The universe holds itself together not through rigid scaffolding, but through constant, subtle exchanges of information between fields. Beneath the equations of quantum field theory lies symmetry. Symmetry in physics does not merely mean visual balance, it means invariance, the idea that certain transformations leave fundamental laws unchanged, rotate space, and the laws remain the same, shift in time, and they remain the same. These symmetries generate conservation laws. Because physics does not change over time, energy is conserved. Because it does not change in space, momentum is conserved. In quantum mechanics, deeper symmetries determine which forces exist and how particles behave. The structure of the Standard Model arises from these mathematical invariances. It is not arbitrary, it is constrained. Symmetry shapes interaction, stability, and identity. The elegance of the equations is not aesthetic coincidence. It reflects structural consistency woven into the fabric of reality. The universe behaves lawfully because its symmetries forbid chaos from overrunning coherence. Over decades, physicists assembled what is now called the Standard Model of particle physics. It describes quarks, leptons, force carriers, and the Higgs boson with extraordinary precision. Every laboratory test so far has confirmed its predictions to astonishing accuracy. It explains why electrons behave as they do, why protons hold together, why radioactive decay occurs. Yet it is incomplete. It does not include gravity. It does not explain dark matter. It does not account for dark energy. And it leaves certain parameters unexplained, values measured but not derived. The Standard Model is both triumph and limitation. It is a nearly perfect map of known particles and interactions, but it also reveals gaps at the edges. Those gaps hint that something deeper remains undiscovered. The model holds, but it may not be final. While quantum mechanics describes three of nature's forces with success, gravity resists unification. Einstein's general relativity explains gravity as curvature in space-time caused by mass and energy. It works beautifully for planets, stars, and black holes. But when gravity is examined at quantum scales, the equations break down. Attempts to quantize gravity produce infinities that resist simple cancellation. The challenge is not minor, it is structural. Relativity describes smooth geometry. Quantum theory describes discrete probabilities. Reconciling them may require a radical shift in understanding. Approaches like string theory and loop quantum gravity attempt this merger, but no experimental confirmation yet exists. Gravity stands as the quiet reminder that our picture, though powerful, is incomplete. The smallest and the largest still refuse full harmony. Somewhere beyond current equations, a deeper coherence may be waiting. If gravity refuses to merge easily with quantum mechanics, some physicists suggest that particles themselves may not be fundamental. String theory proposes that what we call particles are actually tiny vibrating strings of energy, unimaginably small, far smaller than anything we could directly observe. Each mode of vibration corresponds to a different particle. One vibration becomes an electron, another becomes a quark, another might become a graviton, the hypothetical quantum of gravity. In this view, diversity in nature arises not from different objects, but from different frequencies. The universe becomes more musical than mechanical. Reality is not built from points, but from resonances. String theory also requires extra spatial dimensions, curled tightly beyond our perception. Though unproven, it offers a framework where gravity and quantum mechanics could coexist. It suggests that beneath particles lies rhythm, and beneath rhythm, perhaps unity. Another path toward quantum gravity avoids strings entirely. Loop quantum gravity proposes that space itself is quantized, woven from tiny loops forming a discrete network. Instead of smooth geometry, space-time would consist of indivisible chunks at the Planck scale. Just as matter is made of atoms, space would be made of fundamental units. These loops interconnect in a structure sometimes called spin networks. At ordinary scales, this granular structure would appear smooth, just as a beach appears continuous from far away. But at extreme magnification, space would reveal texture. In this framework, black holes and the Big Bang may avoid singularities, replacing infinities with finite quantum geometry. Though still under development, loop quantum gravity offers a different vision of unification. Not vibration, but structure. not strings, but woven geometry underlying everything. When matter falls into a black hole, it appears to disappear beyond the event horizon, yet quantum mechanics insists that information cannot be destroyed. This creates the black hole information paradox. Hawking radiation suggests black holes slowly evaporate over immense timescales. But if they vanish entirely, what happens to the information about everything they consumed? Is it encoded subtly in the radiation, preserved on the event horizon's surface as holographic data, or transformed in ways we do not yet understand? This paradox sits at the intersection of quantum theory, gravity, and thermodynamics. Resolving it could reveal how space-time itself stores information. Black holes are not merely cosmic objects. They are laboratories where our deepest theories strain against one another. And in that strain, new insight may emerge. One proposed solution to the information paradox is the holographic principle. It suggests that the information describing a volume of space may actually be encoded on its boundary surface. Just as a two-dimensional hologram can encode three-dimensional images, the universe itself might function similarly. According to certain calculations, the maximum amount of information inside a region scales with its surface area, not its volume. This idea emerged from black hole thermodynamics and has grown into a broader theoretical framework. If correct, our three-dimensional experience could arise from deeper two-dimensional quantum data. Space would not be primary, but emergent. What feels solid and extended might be the projection of more fundamental information structures. The universe would then resemble not a container, but a code unfolding. Across many modern theories, a common theme appears: information. Entanglement patterns shape geometry. Quantum states encode probabilities. Black hole horizons store bits of data. Increasingly, physicists suspect that information, not matter, not energy, may be the most fundamental element of reality. In quantum mechanics, the state of a system is fully described by information encoded in its wave function. Transformations preserve this information even when particles change form. Computation, entropy, and thermodynamics all intersect with quantum principles. The universe may not simply contain information. It may be information evolving according to mathematical rules. In this perspective, existence becomes process rather than substance, patterns rather than objects, and the fabric of reality becomes something closer to language than to stone. In everyday life, time seems to move in one direction. Ice melts, stars age, memories form of the past, not the future. This directionality is called the arrow of time, and it is closely tied to entropy, the tendency of systems to move from order toward disorder. Yet the fundamental equations of quantum mechanics are mostly time-symmetric. They do not prefer past over future. This raises a quiet question. If the laws do not enforce direction, where does time's flow arise? Some physicists propose that entanglement and quantum correlations generate the arrow of time. As systems interact, they become increasingly entangled with their environment, spreading information outward in irreversible ways. Decoherence ensures that certain states become effectively permanent. The universe's initial low-entropy beginning may have set this direction into motion. Time's arrow may not be fundamental. It may emerge from quantum relationships unfolding across space. Rewind far enough and the cosmos becomes not galaxies and stars, but quantum fields fluctuating at extreme density. The Big Bang was not an explosion in space. It was an expansion of space itself from a state governed by quantum gravity. During inflation, microscopic quantum fluctuations were stretched to cosmic scales. Tiny variations in density became the seeds of galaxies. The large-scale structure of the universe traces back to quantum randomness amplified by expansion. What now spans billions of light-years once existed as subatomic uncertainty. The cosmic microwave background still carries the imprint of those fluctuations, faint temperature variations reflecting quantum origins. In this sense, every galaxy, every star, every atom in your body grew from primordial probability waves. The vast universe emerged from microscopic indeterminacy, magnified by time and gravity into structure and form. Even today, quantum effects may influence the fate of the universe. Vacuum energy, the residual energy of quantum fields, could be responsible for dark energy, the force accelerating cosmic expansion. Observations show galaxies drifting apart faster over time as though space itself is stretching. If vacuum energy is constant, expansion may continue indefinitely, leading to a cold, diffuse future. If it changes, the destiny of the cosmos could alter dramatically. The puzzling mismatch between predicted vacuum energy and observed dark energy remains unresolved. It is one of physics' greatest discrepancies. The smallest scale quantum effects may determine the largest scale cosmic behavior. The expansion of space may not be driven by matter or stars, but by fluctuations embedded in the structure of empty fields. Entanglement suggests that separation is not absolute. Particles once interacting can remain correlated across vast distances. Some cosmologists extend this idea further, proposing that the entire universe may be described by one universal wave function. Rather than independent subsystems, everything could be part of a single quantum state evolving coherently. In this picture, distinctions between observer and observed blur. Subsystems appear separate because of decoherence, but fundamentally they belong to one whole. The universe would not merely contain quantum systems, it would be one. This idea challenges classical notions of independence and locality. It implies that reality at its deepest level is unified, with differentiation emerging only through interaction and entanglement patterns spreading over time. After more than a century of discovery, quantum mechanics remains astonishingly successful and profoundly incomplete. It predicts experimental outcomes with unmatched precision. It underlies chemistry, electronics, lasers, semiconductors, and atomic clocks. And yet, it leaves open questions about measurement, gravity, information, and the ultimate nature of reality. It teaches that certainty has limits, that probability is fundamental, that particles are ripples, that emptiness is active, that observation matters. Rather than closing the book on understanding, quantum physics opens it wider. It replaces rigid determinism with structured possibility. It reveals a universe both lawful and indeterminate, elegant and mysterious. At the smallest scales, reality does not break, it deepens. And in that depth, we find not confusion, but quiet wonder. And so we return gently from the smallest scales. From vibrating strings and woven geometry, from black holes and vacuum energy, from probability waves stretched into galaxies. The quantum world does not demand resolution tonight. It does not insist on certainty. It invites contemplation. Beneath the solidity of your room, beneath the calm rhythm of your breathing, fields ripple, particles flicker, entanglements hum invisibly across distance. The universe continues its patient unfolding without urgency. What seems solid is structured vibration. What seems empty is structured energy. What seems separate may be subtly connected. And you, composed of atoms born in ancient stars, are part of that same quantum fabric, not separate from it, but woven within it. For now, the equations can rest, the mysteries can soften, the smallest scales can drift quietly beyond thought. Reality continues its delicate unfolding, and you can let go. Good night.